Welcome back. Our friends at EFF are constantly standing up for digital rights and fighting endless battles. We at Hope are holding a fundraiser for EFF this year. Please do support as we want to continue support them in whatever battles they are fighting with and helping the global community. Finding bugs in a program gives you the opportunity to research further potential vulnerabilities and exploit them. Our next talk is hunting bugs in your sleep, how to fuzz anything with AFL and AFL Plus by Vron. He's a cybersecurity student and have several projects related to virtualization, containers, IoT security, and binary exploitation. So let's welcome Vron to deliver his talk today.
Hey everybody, I hope you're all doing well. My name is Vron. I am going to be giving a presentation on getting started with AFL or AFL++, or it's alternatively called How to Hunt Bugs in Your Sleep. So a caveat before I move forward. I've given this talk a couple of times before, but I've never used the PowerPoint program I'm using now, which is called Scent, and I've never done a pre-recorded talk. So I haven't written this talk for that scenario, but hopefully it works out just fine. Obviously, if you have any questions, just note them down and I'll be here for the Q&A after the talk is done. So who am I? As I just said, I'm Vron. I've been an undergrad for 12 years because I couldn't decide what I wanted to do for a long time. My actual job is a data scientist. I work for a large international corporation doing Power BI and Tableau and Python stuff for them, basically anything they need data-wise. But that's not really my passion. It's just a job that pays the bills. On the side, I do research in cybersecurity, and I guess you could call it hacking. I would like to pivot to that one day soon, and kind of a way I've started that is at UNC Charlotte we have a hacking club, ethical hacking club, called the 49th Security Division, which this upcoming semester I'll be the president of. Previously I was the executive coordinator. You can look them up. It's a really cool group. We do talks and presentations and projects all related to cybersecurity and hacking. But enough about me. Let's go ahead and talk about what we're going to talk about. So first thing I'm going to do is just talk a little bit about fuzzing. This audience is probably more familiar with fuzzing than other audiences I've presented to, so I'll try to make that brief. And again, if you have any questions of what I covered, feel free to let me know. Then I'm going to go over AFL and AFL++. I'm going to do a demo, and then I'm going to do a couple of other things I don't want to spoil right away, and then wrap up. So let's go ahead and get started with the fuzzing intro. If you don't know, fuzzing is technically just brute forcing. All it is sending data into an application with the hope of getting the application to do something interesting. So you can see there for the second bullet point, I put random in quotes. That's because it's technically brute forcing, but fuzzers have gotten so sophisticated now that how they mutate the data before they try again to insert it into a program it's smarter, let's say. It's smarter. It's not just like A, B, C, A, B, B, etc. When you think of just brute forcing, it's a little more sophisticated than that, so it's not really random, it's pseudo-random. So because of that, the way that fuzzing works, the more time you have, the more tests you can run. So for example, the longest recorded fuzzing job that I could find, if you know of one that was longer, please let me know, was for the Windows Vista operating system tools. Microsoft fuzzed that program or that series of tools for 15 months before they decided to stop. And I think into the 14th month, they were still finding unique crashes and hangs. So that's kind of an idea of you have to know when to stop. We'll talk more about that in a little bit. But people run these jobs for a very long time. I've run jobs for months before. I know people who run jobs for 6 months at a time, some more. So more time is more tests. So the only things you need are, the first two are obvious, something to fuzz and a fuzzer. The last two, which aren't very obvious, are you need hardware. Most people use dedicated hardware for fuzzing for a reason I'll go into in a little bit. And then patience. But like I said on the last slide, you have to know when to stop. So we're going to talk about AFL in a little bit. And AFL has a tool built into it to kind of help you with this. It basically tells you, hey, you've been fuzzing this for a while and nothing interesting has happened, so now might be a good time to stop. And I'll show you that as well when I do the demo. So if you look at the landscape of fuzzers, you can break them into two different categories: dumb fuzzers and smart fuzzers. Dumb fuzzers on the left of the screen, those are what I was talking about earlier, where that is actual brute forcing, where you just go A, B, C, A, B, B, C, C throwing that input or that data into a program, hoping to get it to crash. It doesn't take any feedback. It doesn't take any instruction. It just says, cool, I'm going to throw some random things at this program with a hope to get it to crash. And then on the right side, there's smart fuzzers, which you can break down again into targeted fuzzers and feedback-driven fuzzers. So as I mentioned before, the one we're going to talk about is AFL down in the bottom right. But there are other great fuzzers out there like Peach Fuzz. That's one that people use a lot. Sully is another one that's actually, I think, fully written in Python that people use a lot. Those are called targeted fuzzers, though I think Peach Fuzz has a feedback-driven fuzzing capability built into it. But either way, all that means for targeted fuzzing is just you have an idea of what the input should look like, so you give it a template, and then it fuzzes based on, within the bounds of that template. The feedback-driven fuzzers, which are the ones we're going to look at, what those do is they take the data, they see if anything interesting happened in the program. I'll explain how they do that in a second. And then if something interesting does happen, it takes whatever data it put in to get the interesting thing, it pulls it back, mutates it, and then tries it again, or it adds to the back of the queue to try again. So we can go ahead and start talking specifically about AFL and AFL++. If it's not obvious with the naming convention, AFL++ is just, a newer version of AFL. AFL was written by Google employee Michal Zalewski. If you're familiar with POF, the server analysis tool, he wrote that as well. And he abandoned that project a while back. Abandoned's the wrong word for it. He stopped contributing to the project and encouraged other people to contribute to it. So with these tools, you can start fuzzing CLI tools immediately. There's actually a really impressive trophy case I'll show you here. This is from Michal Zalewski's website. His handle is lcamtough. And these are just a few of the programs that have been fuzzed with AFL that have returned bugs that have now been patched. You'll see names you recognize in here, like the OpenBSD kernel. You'll see Tor. You'll see Ettercap. There's a bunch of things in here. And this isn't all of them. I've found bugs using AFL that are not in this trophy case. You can go to lcamtough's site, lcamtough.coredump.cx, to read more about that. So with some work, you can fuzz almost anything as well, which is what makes AFL and AFL++ so cool, because out of the box, they work on CLI tools immediately, like I said, but you can get them to fuzz a network. You can throw network packets at an application. You can fuzz things you don't have the source code to. You can fuzz things that are non-x86. That takes a little bit of tweaking, but it's doable. So this slide, this is an image from lcamtough's site, Michal Zalewski's site, and what this is a JPEG that was generated by AFL. So this might seem a little complicated, so if you have a question about this, just mark it down and I'll answer it at the end. But what happened here was Michal Zalewski, to prove that AFL was a good feedback-driven fuzzer, he was fuzzing the djpeg library. And the first file he started with, the first and only file he started with, in what's called the seed corpus, the files you use to begin your fuzz job, was a text file. I don't remember what it said. It was something like hello world. And it was just a txt file, just plain text. AFL took that, threw it at the djpeg library, one of the tools, I don't remember which one specifically he was fuzzing. After it got that feedback from the program saying nothing interesting happened, it mutated it and mutated it and mutated it. And I think this took about I think it was 8 hours of fuzzing. And it mutated that text file in such a way that it created what you're looking at right now, which is an actual JPEG. So AFL was able to determine it could get further in the program by, making something look like a JPEG. I don't know how close to exact the header was for the JPEG file after it was mutated to this level, but you could open it and render the file to look just like what you're seeing now. And it ended up getting a bug, or a crash rather, out of djpeg. So how does this work in AFL? For right now, I'm just going to be talking about basic white box fuzzing, which means you have access to the source code. And with that source code, you can compile a program using AFL's custom GCC or CLang compilers. And what those compilers do is they take the basic blocks of each program, I'll talk more about basic blocks in a moment, and it adds these flags to them so AFL can track which basic blocks it's passed, and then it keeps an execution chain of those basic blocks so it knows, did I do this before? Did I access this part of the code before? Is this a new path we found? etc. And again, that'll make a little bit more sense on the next couple of slides. But once you instrument that code using AFL, you have to get some seed files together. Like I said, that's called your seed corpus, like in the previous example with DJPEG. Mikhail Zalewski started with just a text file. You can start with anything. Obviously, you want to have a smart seed corpus. You want to have things like smaller files are always better. Files that you know might do something interesting already. So for example, if in that previous example, Mikhail Zalewski started with a JPEG file, he would have gotten further in 8 hours than if he started with a text file. And as I mentioned previously, because this is a feedback-driven fuzzer, once a new path is found, whatever input found that new path is it's mutated first, then put to the back of the queue to be thrown at the program again. And every now and again, AFL has this cleanup process where it trims files down until the checksum of the execution path is affected. So I'm talking about execution path. That might seem a little incomprehensible. Let me talk a little bit more about that. Well, if you take this image as an example, the code on the left, anyone in the audience familiar with coding at all will recognize that this is just a simple program. You see exactly what it's doing. If x equals 1, execute foo. If y equals 2, execute bar. And then after everything, return. So if you take the case of x and y both equaling 3, the only parts of the code that will be hit are the first check for x, the second check for y, and then return. So on the right, I've labeled all these what are called basic blocks. There's an academic definition for basic block, and I think it's in the assembly code. It has to have one entry point, one exit, and no jumps. I think that's correct, but that's beyond my expertise, let's say. So I've labeled them, and I'm showing you in green which parts of the code would be hit if x and y are both equal to 3. And then at the very bottom on the left, you can see I've put the execution chain there, A, C, E. Those parts of the code are hit. If x was equal to 1, that execution chain, or if x and y were both equal to 1, the execution chain would be A, B, and E instead of A, C, and E. So how AFL determines if it's found a new path is it takes that execution chain and compares it to the previous execution chains that have already been found. And if they don't match, it hashes them and then creates a checksum. And if the checksums don't match, it says, oh, we found a new path. That means the input was interesting. Let's take whatever input found this new path, let's reintroduce it to the queue, and let's throw it back at the program again to see if we can do something else interesting. So this is more just for your reference, but this is effectively what the algorithm for AFL does. It's basically what I've already explained. It takes a candidate, throws it at a program. If something interesting happens, it mutates it and puts it to the back of the queue. If I didn't make that clear enough earlier, when I'm saying it finds something interesting, AFL determines something interesting as either a new path, a hang in the program, or a crash. So I'm going to do a quick cut to a demo. Fortunately for me, I don't have to do this live. I've previously done it live, so nothing should go wrong, but if something does, I guess that's cause to be alarmed. Okay, so I'm going to run through a quick demo of AFL to show how easy it is to get started. Let me increase the screen size, or the text size here rather. Because I work with students a lot, I write a lot of scripts to help people get started for people who aren't as comfortable compiling from source code. So I've actually written a script to get AFL downloaded and installed on your system, but I've also set it up so that it shows what commands are being run. So all you have to do is grab it from LCAMTough's site, and this script of course will be available. It downloads a tarball version of the program, and then you just sudo make, or you actually are just supposed to make and sudo make install. I don't know why I wrote sudo there. And that's going to compile for us and install it on our system. Very straightforward. If you've done this before with a program, this isn't going to be an issue for you. And like I said, if you haven't, I can make this script available. So anyway, AFL is now installed. As I mentioned before, or I should have mentioned before, sorry if I didn't, AFL comes with a bunch of different tools as well. And there are two really important ones, which are Test Minimizer and Corpus Minimizer, which I will demo here. Okay, that's installed. That's good. So next what I'm going to do is I'm going to install an old version of SQLite that I've worked on before. This is really simple. All this is going to do is create some directories and then download the source code for SQLite 2 and install it on my system. I'm going to take the test cases that AFL provides for you, and I'm going to use those in my example. I'll show you those before we actually get started. Anyway, the only main thing that matters is once this command runs where it installs the SQLite source code, you're going to see that I've changed the CC options so I can compile SQLite using AFL's C compilers. I think that's about to pop up now, and I'll go over what the output looks like. Yes, so here you see I'm running configure from within the SQLite directory, and I've changed the C++ compiler to AFL's G++ compiler. So that their wrapped compiler is what I'm going to use. That's what's going to insert those flags so AFL can keep track of the execution chain. As this compiles, you're going to see, well, it's hard to see because it's going by quickly. You'll see AFL CC, AS for I think that's the linker. But either way, this is being compiled with AFL right now. So those flags can be inserted so we can much more easily fuzz the program. Well, I guess it's mainly so we get better feedback whenever we fuzz the program. So the test cases AFL comes with, it comes with some examples here. You can see there's all different kinds of files and formats and whatnot. And what I did in that script I just showed was, let me cd in the targets directory, SQLite. I moved them into a folder called in. There's a SQL file, there's a text file, there's image files, there's all kinds of things. And these are the things I'm going to throw at SQLite to try to get some interesting crashes. And if nothing happens, AFL will mutate those files and it will try to make something interesting happen with the mutated version. But let me talk about SQLite first. Anyone familiar with SQLite or just SQL in general, you'll know that to create a table, you just run create table and then table name. It doesn't make a difference what it is. And then I don't even know if I need a parameter there. Okay, did need a parameter. And then there you go, the table is created. So I'm going to drop that now. Okay, so one of the cool things about SQLite though is that you can throw commands at it from a file. So if I were to run something like SQLite and then I were to, oh, sorry, I guess I have to create the file first. Let's move it in here. File, and then I want to run SQLite. Great, awesome. So we got no errors there. So if you didn't pick up what I was doing, basically I was just taking a SQL command, putting it into a file, and then directing it into SQLite. That doesn't work if you don't pipe it in, obviously. It just runs SQLite and then never gets to the second part of the instruction. That's pretty apparent. Now, the reason why I'm bringing that up is because how you configure something to be fuzzed with AFL does make a difference. So let me go ahead and just show a basic fuzz job really, really quickly. I might have to make this a little bit smaller actually. So I'm just gonna, hopefully that's still visible. So all we have to do is we run AFL fuzz, use I for input, that's a required flag, O for output, also a required flag. And if you don't remember, I created two directories here called in and out. So that's what I was using for those. I'm not just choosing those names arbitrarily. They're the names of the directories in this directory. The in file, the in directory rather, has all of our test cases and the out directory is empty. And we're gonna just put it in the path to our target, which is SQLite. And then what AFL does is if you use this parameter, the two at symbols together, it replaces those two at symbols with the desired input. So remember how I just ran that command with SQLite where I didn't have the redirect operator? That's effectively what this is saying. This is saying fuzz this, but run it like SQLite plus whatever the fuzzed input is on the command line. And you'll see, ignore all that error output for now, I'm going to talk about that in a second. You'll see that what happens is we have no new paths. We have 40 total paths because that's the number of files we started with, but we have no new paths. And this will run forever. I've tried it for a very long time, and nothing new will happen because of the way we ran it. So you do have to be careful about this. If you're running SQLite, or any program really, if you remove those at symbols, AFL tries to pass the input into the program like what we saw with the redirect. So hopefully that's clear. Again, normally when I do these live presentations, people can ask questions freely because it's difficult to tell if this is being explained well or not unless you can see audience feedback. But if I put those @ symbols, it's saying run this entire command with the input on the command line. If I remove them, it says run this command and try to pass the input into the program. So if I just run it like this, again, ignore that error output. We'll talk about that in a little bit. You'll notice that our total paths start increasing significantly, and in just a few seconds, we'll hit some unique crashes. But anyway, while we're waiting for that to happen, I'll go ahead and just talk a little bit about what you're seeing here on the screen. So process timing, that's fairly straightforward, I think. It's obviously just saying, just statistics about your fuzz job, about how long it's been running, when the last unique crash was found, etc. Overall results, sorry. That's also fairly straightforward. Now we're seeing some activity here. So the paths are what I talked about earlier with that execution chain. That's what's being kept track of there. The unique crashes is straightforward. Unique hangs is straightforward. What's not as straightforward is the cycles. So you remember I mentioned earlier that AFL has a built-in tool to help you determine if you have been running your fuzz job for too long. A cycle is complete whenever all test cases in the queue are gone through. So this number will increase, but it will turn yellow whenever all test cases in the queue have been gone through and no new paths were found. So basically it's saying, okay, let's say for example, I've got a queue of 100 files. If it goes through all of those and this number doesn't increase at all, this will turn yellow, signifying, hey, you've probably done all you can with this. Cycle progress, this is, cycle progress, this is exactly what it sounds like. Stage progress, I didn't go into this either because just for time purposes, but AFL has, I think 6, maybe 8. Anyway, more than 5 different paths different stages that it uses to manipulate a file. The one running right now is Havoc, which is what it sounds like. It's pretty much just not a random mess, but a pseudo-random mess. But there's other things like bit flipping, arithmetic. Again, you can read more about that on AFL's documentation, but these are all just methods of manipulating the file. There we go, bit flip, arithmetic, and they go in a certain order whenever it's working deterministically like this. I haven't set it to do anything random. I'm actually not going to explain the remaining fields, and the only reason for that is because of time, but frankly, those fields aren't as interesting unless you're super technical. The ones I've gone over already are all the ones you'll need if you want to find bugs and crashes with AFL. So I'm going to go ahead and stop this by hitting Control-C. And let's take a look at what one of these crashes looks like. So let's go into the, as I mentioned before, we had the in directory, which had our test files. Now we have the out directory, which was empty, but it shows a bunch of other things as well. Whoops. These are all the unique crashes that we found. Let's go ahead and open one up. I'll just cat one out. I think that's probably best. Let's see what our options are. 28. Why not? 28 seems good. Okay, so this is interesting because as we said earlier, we can pass data into SQLite from a file. So what's cool about this is even though we didn't have a lot of test cases that looked anything like SQL commands, AFL has created these malformed SQL commands for us that are causing SQLite to crash. So if I were to run SQLite and then pass in this file, whoops, we get a crash. And so what that's doing again is executing these lines in SQLite. And what we have here is, there's some information, some debugging information, but either way we've crashed the program. This is actual data that crashes, or an actual file that will crash an instance of SQLite. And it really is that simple to get started fuzzing with AFL. All you have to do is, like I said, either take the scripts that I have or download AFL or AFL++ itself. If you download AFL, you get it from LCamTough's site. If you download AFL++, you get it from GitHub. But it's that simple. You can start fuzzing in less than 5 minutes. If you already have a target available, that is. So I want to talk about 2 more things. Like I mentioned, it's the Minimizer series from AFL. So let's go ahead and say, let's look at our input directory. Let's list it out like this. So all of these files, you can tell by the bytes here in this column. In this column. These are all fairly small files anyway. Small movie is actually a little too big, so is this one here. Small archive. But these are all fairly small anyway. But if I want to take the seed corpus I have, the initial test files I have, and weed out the ones that either duplicate the execution chain or don't do anything at all, I can use AFL's corpus minimizer series or functionality. And how you do that is you have to give it an input file, which is we're going to use in, and then you give it a new output file. It could exist already, but just make sure there's nothing in it. And then run the command, or I'm sorry, write the path of what you want to fuzz. So when we do that, you can see that we have 40 files, just like we had before. You know that we have 40 test cases. And what this is doing is it's taking them, running them all through AFL fuzz. Running them through AFL fuzz and trying to determine what files are duplicating the execution chain and which are unnecessary. And you can see now we've narrowed it down to 16 files that do something interesting. So if I had started with this, I would have actually found those crashes much more quickly because I had, 24 files that were just doing duplicate work. So it's always good to run this. In fact, you can stop a job, you can take the crashes you found from here, and then run those against the program in the AFL corpus minimizer to go ahead and start the job over with really grand results. Well, hopefully grand results. There's another part of AFL called the test minimizer, which what that does is it actually just focuses on a single file. So let's say from my new in directory, let's take smallarchive.cpio. What I can do with that is I can run AFL tmin for test minimizer. I say, what file do I want to start with? I want to start with smallarchive.cpio. What file do I want to end with? This isn't a directory you're creating, this is an actual file, so we'll call it new in, new file. And then you write the path to the program you want to fuzz. Now what that's doing is that's actually clearing out bytes that don't seem to do anything to the program additionally. What do I mean by that? Well, if you look down here at the bottom, it says file size has been reduced by 35%. It's been reduced to 332 bytes from wherever it started. I'm not sure where that was. And it determined that by actually running that file 340 times against the program to see what can I remove without affecting the execution chain made by the original file. And this is meant specifically to make all your test cases smaller for the reasons I've mentioned. Smaller test cases and more targeted seed corpuses are the best way to get fuzzing results. So you can write a quick script to run AFL tmin against all of your current crashes if you want to start fuzzing again, and basically have a more successful, a higher chance of success finding crashes. So that's all for this demo. I'm going to cut back to the presentation now. So that's how easy it is to get started with AFL. Like I've mentioned before, AFL++ is just a fork of this. The actual fuzzing algorithm has been updated very slightly, so you can get the same speed and performance out of AFL or AFL++, but AFL++ has some added features that aren't exactly built into AFL. You can make them happen, but you have to tweak it a little bit. But like I said, the work's already done for you with AFL++. Another benefit to it is that it's an active community. So if you find something interesting, you can contribute it to the project as well. And the pull request will probably be accepted depending on what the feature is. So some of the things you can do with AFL and AFL++ is you can do what's called black box or non-x86 fuzzing. Those are actually both done the same way. All that means is you don't have access to the source code, so AFL will fuzz it anyway. It will use a feature of QEMU called user emulation mode to not only execute the program, but to determine when a crash has been found. You can also do parallel fuzzing. Again, you can do this in both AFL and AFL++, and all that means is you can have one main fuzzing job, which is called the master, and then you can have several slave fuzzing jobs, as many as you want, really. The master fuzzing process, that fuzzes deterministically, meaning it's making the changes in AFL's algorithm that you would expect. It's using all of the stuff we've discussed previously, but the slave processes are actually throwing randomized input at interesting looking test cases, mutating them randomly. There's other things you can do in AFL, like you can make graphs, there are add-ons and plugins for AFL and AFL++. Overall, even though the last demo I did was technically AFL, I'd recommend you go ahead and switch to AFL++ unless you really are in a resource-constrained environment. So I want to talk a little bit more about non-x86 fuzzing, and the reason for this is because it's something that I've worked on with a little bit of success. And this is a cool feature. I started doing this with AFL and then I switched to AFL++, which is why I kind of use them interchangeably in my presentation, because I still have processes that are running with AFL. All new processes I start are running with AFL++. Black box, like I mentioned previously, and non-x86 fuzzing are done the exact same way using QEMU. It's significantly slower, and there's a problem where if you're trying to do this on an x86 machine, you need all these QEMU dependencies, and that brings me to something called Fox, something I've called 5 o'clock shadow. Basically what this does is it bootstraps all of the annoying stuff you need for QEMU already. The only limitation to it is that you need a firmware image that you can extract with Binwalk to get it to work. And if you have that, you can get started fuzzing with Fox and AFL++ in practically no time at all. I currently have a repository of about 280, maybe closer to 300 gigs of firmware images I've downloaded from Linksys and D-Link and even some OpenWRT and even some ASUS router stuff that I pass through this to fuzz as much as I can. As I mentioned previously, as long as you have the hardware, you can really fuzz as much as you want. So what I'm going to do now is I'm actually going to cut to that demo before we wrap up. Okay, we're here for the Fox demo now. Sorry about the aspect ratio on this. I'm using a VM that isn't allowing me to go full screen in the way I want. So we're just going to have to work with this. Let me increase the screen or the text size a little bit. So what I've done here, I've talked a little bit about how you can start fuzzing x86 command line tools immediately. I talked a little bit about how you can fuzz network applications and web applications using AFL++. I don't have time to demo that today. But the other thing I talked about was black box and non-x86 fuzzing. And AFL accomplishes this by using QEMU, user emulation mode, as I've probably mentioned before in the presentation. And using that is really, really simple. The problem is you sometimes need library dependencies for QEMU to accurately use user emulation mode. You also need to set a couple of environment variables. Things like QEMU LD prefix is one. You have to set that to a directory that's housing the library files for the architecture you're trying to fuzz on. And I got so frustrated with this because I came into contact with a library of about 300 gigabytes worth of firmware for things like routers and cameras and stuff like that. And most of it was either ARM or MIPS, but none of it was x86. So I decided to go ahead and put together I guess it's really just a script called Fox, which deals with all the nonsense for you, the things that you would have to figure out on your own normally if you're trying to bootstrap AFL to work with non-x86 files on an x86 machine. And so I'm just going to show how easy this tool makes that. What I've done here, I have two firmware images from ASUS. I think these are both router images. I've unzipped the GTAX 11000. Let me go ahead and go into that directory. And if you've ever used Binwalk, I've opened this with, I extracted the firmware with Binwalk, so you'll know there's a couple of unnecessary folders before you get to what you need. So let me go ahead and CD to where I need. Okay, that should be it. So to make this easy, if you start in the directory that has the basic home directory files, or I'm sorry, root directory files, such as bin, home, etc., the lib directory is what you need the most. But if you start here and you run Fox, AFL and Fox will take care of everything you need. So let's go ahead and look at some stuff here we might want to fuzz. Actually, I might have to make the text smaller for a little bit. Sorry about that. So I'm in the bin directory, and of course, there's stuff you recognize here. Let me make it all executable as well. There's stuff you recognize. There's bash, there's busybox. If you've done anything in the embedded space, you know all about busybox. But if I go to run one of these commands, like let's say bash, I'm going to run file on it. It says it's an ARM executable right here, which means if I try to execute it, like I do here, I get an error saying no such file or directory. Basically, it's telling me that I don't have the library dependencies to run this because, well, I haven't set it up to do that. This is an x86 machine. It's dependent on ARM library files. So if I go into the directory that has the lib file, the library file, and I export the environment variable QEMU LD prefix and set it to this directory, and then I use QEMU ARM to run bin bash, I'll be able to execute the ARM version of bash on my x86 hardware. So effectively, this is all that Fox is doing. It's doing a couple of other things, like it's automatically using the corpus minimizer and test minimizer to make your life easier so you don't have to worry about that. It's also keeping track of everything that you have fuzzed before. Like, for example, let's see what I have here. So every time it fuzzes a new architecture, it creates a directory for that architecture. If you look at MIPS, you can see it's named all of the things I've fuzzed, and it's kept part of their checksummed value. The reason for this is because, again, if you're familiar with BusyBox, you'll know that everything that's a symbolic link to BusyBox has the same checksum as BusyBox. So if you're fuzzing something that's part of BusyBox, and you've already fuzzed BusyBox, Fox will just tell you, hey, look, you've probably used something to fuzz this program before. It looks like the same program, and that gives you information that can help you improve the details of the fuzz job that you're going to do. If you look here, you'll see that for this MIPS version of BZCat, I've got a whole, it looks like 46 unique, maybe 47 because I think it starts with 0 unique crashes. I have hundreds of these now. And like I said, the thing that I found the most frustrating was getting things set up to start fuzzing non-x86 files. So let's just go ahead and show you what Fox does to make this a little bit easier. We're going to fuzz bash. It should give me a warning. So I want to say fuzz new binary or directory of binaries. I planned on adding the feature to fuzz an entire directory of binaries all at once, but the reason why that's not implemented yet is because for reasons we've talked about before, namely that you need to know the format that the program you're trying to fuzz accepts input. You really should target your input a little bit better than just taking one, like just using @@ on everything. So for example, gzip does require a command line argument. So if you do gzip @@, you're going to have more success than not having anything after gzip. But like we saw with SQLite does not take a command line argument. So if you have that @@ symbol after SQLite, you will just find nothing. You could run it for years. You'll never find anything. So that's why that feature hasn't been implemented yet. So let's just go ahead and do a new binary. Let's point this to bin bash. There you go. I got the warning saying you fuzzed this before. It keeps a list, like I said, of the checksums of all the files I've fuzzed. Like I said, I have 300 gigs of firmware images, and if they're all running the same version of BusyBox, I only want to fuzz it once. But let's go ahead and override that for now. We're going to fuzz it anyway. And I might skip this part of the video because this could take up to 5 minutes. But basically what this is doing is Fox is extracting the architecture of the file I'm trying to fuzz, and then it's compiling AFL's QEMU mode to run on that architecture. So if I leave this video up long enough, you'll see in this tiny text, maybe I can actually make it bigger now, you'll see that it says ARM quite a few times. If I had targeted a MIPS binary, it would automatically compile AFL to fuzz MIPS binaries. I'm probably going to cut the video now and just cut to the part where the fuzz job actually starts, so we don't have to wait on this to compile. Okay, so AFL's been compiled to fuzz ARM. I'm going to make this text smaller because I think you need to see this. So it stops right before the fuzz job begins, and it says, what would you like to make as the command line arguments? Now, because I'm running bash, I know I'm not going to need any command line arguments, so I won't enter anything. But like I mentioned in the example earlier, if I was running gzip, I would want to put an @@ here, or if I was running gunzip, I would want to make @@.gz. Because remember, this sorry, back arrow doesn't work. This @@ gets replaced with the test input. But in this case, I'm just going to pass the input directly into bash. So you can see the corpus minimizer's already worked. We start with those same 40 test cases, and it was minimized to 16. Because it's black box fuzzing, it doesn't have access to the source code. So I determined the best way is just to start with some kind of seed corpus. In this case, I'm using the AFL test cases, and then just minimize it per fuzz job, just to get as close as we can to something usable. Obviously, if you know what you're fuzzing, you can start with something a little more targeted. But if you're going to be running this for a super long time, these binaries aren't big enough for that to really make a difference. You can start with something like this, and AFL will do the work for you. Always a better idea to start with better test cases, though. So you saw how easy it was before to get started with AFL, and now if you just use this script, it's available obviously on GitHub for free. You can get started fuzzing non-x86 binaries as well as this black box fuzzing anything, really. You can fuzz black box x86 programs using this as well. It doesn't have to be non-x86. It's just designed to work around some of the more annoying things about fuzzing MIPS and ARM binaries on an x86 machine. And at this point, I've only gone through like 10 gigs of those 300 gigs of firmware, so feel free to reach out to me. I'm happy to give that to anyone. And if you want to start fuzzing them, finding some crashes, doing some tests, some analysis on the crashes, that'd be cool. I'm probably going to leave this one running, but that's it for this demo. So that's pretty much it for the presentation. To recap, AFL is a feedback-driven fuzzer that every time it finds something interesting with a particular input to a program, it mutates that input and then tries again at a different time. You definitely want dedicated hardware running at as much capacity as you can to be effective at fuzzing. What's great about using AFL and Fox and all this stuff is that there are companies like Google that are constantly fuzzing all the time, and you can't compete with Google. So fuzzing something like phone applications, which you can do with AFL, or fuzzing something like non-x86 binaries, firmware images, like what I've done here. All of that can be done, and it's relatively a low barrier to entry. In fact, everything's free. The only thing you need is, like I said, dedicated hardware. But it is cool to find a bug in some of your favorite programs. And that's pretty much it. Thank you very much.
So thank you so much, Ron, for this amazing talk. We have a few questions now that the audience would like to ask you. The first question is, what's the difference between AFL and AFL++?
Okay, I can answer that. First, I realized I didn't say this at the end of my talk, but thank you, Hope team and everyone, for giving me the opportunity to do this. I appreciate that. So sorry, I forgot to add that to the video. The difference in AFL and AFL++. AFL++, I think I mentioned it's at one point in the talk, after Mikhail Zalewski stopped contributing to AFL, he stopped updating it. AFL++ is a fork of that. And that team, it's a group of people who are passionate about AFL and kind of fuzzing in general. They've added a couple of commonly asked for features into it. So, for example, network fuzzing with Preeny. It used to be this big workaround with AFL. You had to download AFL, you had to edit some of the code, you had to download another program called Preeny, get it to work with AFL. And AFL++ is a fork of AFL that has that built into it automatically. Excuse me. They claim to have made some differences in the fuzzing algorithm, but it's not a noticeable difference. They said this was for performance reasons. I'm not even positive what all code they changed, but effectively it's the current active version of AFL. Major difference if you're doing something like I mentioned in the video in a resource constrained environment is that AFL++ is much bigger than AFL, but nowadays that's typically not an issue. It's not so huge, you can't use it.
All right, there's another question. So the person missed the initial part of the talk, but he has a question. Where is the repo of your initial fuzzing input?
So when you download AFL, oh, sorry, I was reading the new question. So when you download AFL, if you go into the AFL directory, there's also a test cases directory. And in there's a bunch of other subdirectories that they hold different kinds of files, zip files, image files, video format files, SQL files, text files. And in that script that I played in the talk, all that's doing is looking into that test cases directory and then recursively looking into that test cases directory and copying everything that's of type F, just a regular file type, not directory, and copying it into the in directory. So those are, just for demonstration purposes, those are the test cases given to you in the initial AFL repo. I think I also mentioned near the end there at the talk that it's always better to have a more targeted seed corpus whenever you're starting. But for this, to make it simple, and at the end, wherever I'm fuzzing, firmware images or firmware binaries they're really small, I'm just taking all the test cases AFL already gives you and then throwing them at the binary.
We have another question, sorry. Did you watch the talk yesterday on binary recompilation? Seems like it could be used to add the instrumentation that the AFL compiler adds, but right into pre-compiler binaries.
Honestly, I I didn't see that talk, which is a shame because that sounds really, really interesting. So I'm not positive about that. I've spoken with someone a while back. We were talking about kind of utilizing fuzzing for CTF stuff for a CTF team we have. And they've mentioned using symbolic execution to help with fuzzing. I don't know if that is going to head in the same direction. Looking at the question, I'm not sure. I'll have to look more into that. I'm not positive though.
All right, no worries about that. Well, if the audience has any more questions, please send it across in the Matrix chat. And for now, thank you, Ron, for this wonderful talk. It was really amazing. For our audience, please do check out our schedule. We have multiple workshops and villages running in parallel. So yeah, we will be back in another 10 minutes for the next talk. Until then, stay safe and thank you so much.
Thank you.